real analysis class. 2020. Well, I guess you have more classes starting in your diploma program now, right? You have complex analysis starting sometime soon, maybe algebra. I guess you believe that this means that you have less homework for analysis since now you have more classes to juggle, right? No, that's not true. You have more homework, okay? So I don't know how I'm not sure how you will manage, but you figured it out. All right, so this is lecture number 7. We are going to continue our discussion in the Littlewood's principles that we started in the last class. And we will start talking a little bit about LP spaces. Okay, so this is the plan for today. And for next Thursday, I hope to continue and finish the discussion on LP spaces. So by the end of this week, we will have this new, knowledge or machinery of LP spaces. I'm sure all of you know, but at least for the sake of completeness of our course, you have been introduced to LP spaces. And then we will have a bunch of nice problems to think about. Okay, so let's start with some review of this, what we meant by Littlewood's principles. This was just a nice way to summarize some of the changes, some of the improvements that we went through when moving to Lebesgue measure and the Lebesgue measurable functions from what we had before, from well-known things like cubes, continuous functions, and uniform convergence, right? So we started kind of summarizing in the sense that every, measurable set is essentially, or is nearly, that's the word I used, a disjoint, a union of cubes, let's put it this way. Every continuous or every measurable function, and here we are, let's say, we are on RD, okay? Don't forget that we are working in RD with the Lebesgue measure. Every measurable function is nearly continuous. And the third one was that every, let's say, convergent, pointwise convergent sequence of measurable functions is nearly uniformly convergent. Of course, these are imprecise statements that we want somehow now to make them precise. We have discussed in the last class, I guess, the number 1 and the number 3, right? The number 1 comes from this, this number 1 we kind of summarized in a proposition that looked like this, right? The proposition was that if E contained in RD, say, is measurable, well, let's say with a finite measure, I guess, then E is almost a disjoint union of cubes. So then there exists, let's say, there exists a certain set F, which is the disjoint union, almost disjoint union of cubes. Okay, so the cubes are almost disjoint. Such that the measure of E, the symmetric difference, was less than epsilon, right? Then, perhaps I should say here, given epsilon, there exists a collection, an almost disjoint union of cubes such that the measure of the symmetric difference is small. Okay, so this is essentially what I mean. We can understand the first statement as this: every measurable set is nearly a union of cubes. Well, we have seen that the Lebesgue measure has these irregularity properties, right? We have seen that every measurable set can be approximated by open sets from the outside and by closed sets from the inside. If you want to take actually if you want to approximate by closed sets from the inside, you can even consider a countable union of closed sets from the inside, and the measure of what's left is 0. Okay? So if you want, you can do this in the sense that, remember, this regularity. So you have this regularity of the Lebesgue measure in many distinct settings, but for example, every Lebesgue measurable set, you can actually write it as a union of compacts, Kn, union of certain set Z of measure 0. So Kn's are compact sets, and the measure of Z is 0. Okay? So it's kind of the simplest decomposition that you can take. You know, you just take a bunch of compact sets, and then what's left is a set of measure 0. Now, of course, it's a countable union. So if you want a countable union of closed sets, it's not necessarily closed anymore. But this is a guy in the Borel sigma algebra. Okay? So it's somebody in the Borel sigma algebra, union a set of measure 0. All right. So this was the first one. And that third one there was this theorem of Egorov that, again, said the following. So what we proved was the following. So let E contained in Rd be a measurable set, measure of E finite, and Fn a sequence of functions defined on E such that f of Fn converges to F pointwise. You can even say almost everywhere on E, okay? Then the claim is given epsilon bigger than 0, there exists a set F epsilon contained in E, F epsilon closed, such that the convergence is uniform on this set epsilon. Well, this I closed. The measure of E minus this F epsilon smaller than or equal than epsilon, and such that Fn converges to F uniformly on this F epsilon. Okay. So this is the claim. Every time that you have a set of finite measure and you have a sequence converging pointwise to F, if you give me an epsilon, you can find a closed subset inside your E, very close, you know, such that the measure of the difference is smaller than epsilon, and such that the convergence is uniform on F epsilon. Okay. So this was the second one. Yes. Now, my goal is to prove, so this is the understanding of this third principle here. Our goal now is to provide an understanding of the second one, that every measurable function is nearly continuous. Okay, and this is, let me perhaps make a digression and talk a little bit about approximating functions, you know. But we know that a measurable function can somehow be approximated pointwise by simple functions. Okay? So remember that we define these simple functions as things of the form, let's call phi was sum of ak, characteristic function of a set ek, k from 1 to n. So it was a linear combination, a finite linear combination of characteristic functions of measurable sets. Okay? In general, simple functions is the object that you have to use when you are working in a general measure space. Well, in a general measurable space, you have the set, you have the sigma algebra, and you have the measurable sets, and you can take finite linear combinations of characteristic functions of measurable sets. You know? When you are working in RD, there are some special measurable sets. You know, I mean, the measurable sets may be very crazy, right? But there are special sets which are very simple. For example, cubes or rectangles. And you may actually try to construct a class that lies inside this one, but when you take just characteristic functions of things which are very, very easy. For example, cubes. So for the purpose of our discussion today, let's call these functions step functions. Okay? Let's call a step function a function psi, which is just looks like this one. So it's a finite linear combination of characteristic functions, but now of cubes. So qk is now cubed. Finite linear combination with some coefficients of characteristic functions of cubes. I'm not saying that the coefficients are all different. I'm not saying that the cubes have to be disjoint. Let's not worry about this for now. So just take cubes. They might overlap, characteristic function of the cube, and then you take a coefficient. That could be, doesn't have to be different, okay? So let's call these functions step functions. So they, of course, the class of step functions lies inside the class of simple functions. Some books will define step functions with characteristic functions of rectangles. That's fine too. But for our purposes, I think cubes is even simpler. Okay? So remember, I remind you a construction that we did. Let me remind you, let's come back, a little bit of a digression here. Digression. I recall to you that whenever I had a positive measurable function, we could construct a sequence, you know, phi1, phi2, phi3, blah, 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 of functions which were less than f, such that this phi k converged to f pointwise, everywhere. Right? Remember that we constructed this, and the way that we constructed was kind of dividing these things here dyadically, right? So we made this dyadic decomposition here, and at each step we would finish in a certain height n. At every step we would go to n plus 1 and even subdivide the intervals here dyadically. So we constructed this sequence here, and this converged to f pointwise everywhere, and it was a monotone increasing sequence of, you know, these phi k's were all simple functions. Okay? Now, whenever you have an f which is not positive, not non-negative, in general, what you can say is if you have an f, you can apply this argument with the positive part, and you can apply with the negative part. So if your function f has a sign, you can construct a sequence that approximates the positive part and the negative part from below. So what you have is a sequence of simple functions phi k, simple again, phi k approaching f everywhere. But now what you can say is that the modulus of phi1 loses to the modulus of phi2 that loses to the modulus of f, you know, because phi1, I mean, the positive part will lose well, you do the procedure for this one and for this one separately, and then you subtract them up. Okay? So these inequalities here will imply this thing in the general case. So you can construct a sequence for any given function of simple functions that approximate your function pointwise such that the absolute values of these functions form an increasing sequence to your f. Okay? All right. Now, suppose that I want to do this, and this is general. So this is for general measure spaces, right? So now let's come back to the setup of RD. And I want to convince you that in RD, we can do something similar with step functions. Okay, so let's try to do something similar to this, but now with step functions. So let me propose to you the following proposition here. Proposition 1 of the lecture today. Let me write it in a proper way. All right. So the proposition that I want to prove to you is the following. Let f be a measurable function on RD. When I say measurable and I don't say anything else, I'm always referring to the Lebesgue measure. Okay? Then the claim is then there exists a sequence of step functions as I defined here. Let's call it psi k, such that psi k approximates such that I'm going to put here psi k goes to f pointwise almost everywhere. Okay? Pointwise almost everywhere. Okay, so you know. Compare this result to what we had before, you know. You see that there is a trade-off here. I'm changing thing. Nothing is for free, completely for free. Here I had a sequence of simple functions that approximated f monotonically, right? And everywhere. Here I want to change my functions to even simpler functions. So I claim to you that I can actually approximate any function by step functions. I claim that we can approximate pointwise almost everywhere. So I'm not claiming that it's going to be monotonically, and I'm not claiming that it's going to be everywhere. But let's just prove it that I can approximate pointwise almost everywhere. How we would argue with our result like this. And then you guys can think about at home if this is really the best that we can do. So you see, this is really nice in the sense that when we talk about LP spaces and the classes of functions which are dense in LP spaces, you have the continuous functions, you will have the simple functions and the step functions, you know. If in your LP, if P is not infinity. We'll talk about this in a minute. Okay, so let's see how we would prove such a statement. And I suppose we would go somewhat like this. I wanted to start with the first setup that we already know. Okay? We already know that we can approximate my function by simple functions in a monotonic way. Now, remember, we were working in general measure spaces here. Okay? So we didn't have this notion of metric, of compact sets, and so on. But if you are working on RD, you know, our construction, if you remember, we divided diagonally here this y-axis up to a height n, and then we considered the pieces of the function that were inside each of these intervals, right? maybe this is not a good drawing, but maybe I should go back and do something. We would consider the pieces of the functions that lie inside these intervals. And then at each step, we would move n. This would be phi k, right? So we would move this k to k plus 1, and then we would subdivide the pieces here in a dyadic way. But if you are in RD, you can not only increase these things upwards, but you can also truncate these functions by balls, okay? So my point is, if you you will start with the usual construction. That you can approximate this by phi k simple. And monotonically increasing, like we did. By considering, I actually want to consider phi k, I'm considering phi k tilde to be phi k times the characteristic function of the ball of radius k. So I'm also going to truncate these functions by balls. So I'm going to take a small ball here, the first step, and then a second ball here, and a third ball here. So I kind of truncate my functions up and down here. So if you just consider the truncations of functions by the ball k, of course, you still have the same properties. You still have the convergence to f everywhere, and that is still monotone. Okay? So by considering this, you can assume that these phi k's are compactly supported. Okay, so they're supported in the ball. And then you make. Okay, so now my thing is, well, the sequence of simple functions is approaching f. If I want to approximate f by a step function, I could as well approximate these guys by step functions here. So this is the idea. If I can approximate a simple function by a step function, then I would reasonably believe that I can approximate f by a simple function, by a step function. So the idea would be to, well, let's say, I want to convince you the following. It would be sufficient to construct a step function psi k such that psi k is almost equal to phi k. Almost equal in which sense? Such that the measure of the set where psi k is different than phi k is smaller than, let's say, 1 over 2 to the k. I want to construct a step function such that the measure of the set where it differs from the simple function phi k is a small number, 1 over 2 to the k.
We can use the approximation by finite cubes.
Yes, we are going to do this. But before properly doing this, I want to justify why this is sufficient. Give me 2 minutes, and then we're going to go there, right? So I claim to you that it's sufficient to do this. In fact, let me just conclude this reasoning. In fact, if we could prove this, so if you let these sets here, if you call these sets EK, the set where psi k is different than phi k, the measure of EK is less than 1 over 2 to the k, they add up, right? And there is a result that I assigned to you on the exercise list called the Borel-Cantelli lemma, which if you have a sequence of sets such that the measure adds up to a finite number, then almost all the points on your whole space belong to a finite number of those subsets. Okay? So if we could prove this by the Borel-Cantelli lemma, almost all points x in Rd belong to only finitely many of these sets Ek. Well, but then if a point x belongs to just finitely many sets Ek, it means that once you are past these finitely many sets that it belongs, it will not belong to the sets starting from some k, and then it will be equal to, your psi k will be equal to phi k, and then phi k converges to f, your psi k will converge to f as well. Okay? So for every one of these points, this would imply that psi k converges to f almost everywhere. And I'm throwing in the almost everywhere here just because of this, because I can only conclude the Borel-Cantelli. The conclusion from the Borel-Cantelli lemma implies that almost all points belong to finitely many of these sets. Okay. So this is okay. We have seen that's enough to show that I can construct a step function which is very close, which is almost equal to a simple function. But now, a simple function is just a linear combination of characteristic functions of measurable sets. So it is kind of sufficient with the finite number. Okay? So I will claim again, so it is sufficient. It is sufficient now, given a measurable set E, just given a measurable set E, to construct a step function phi, step function psi, such that it is very close to the characteristic function of the set E, such that the measure of the set where psi differs from the characteristic function of E is smaller than epsilon. Given epsilon bigger than 0 and a measurable set E to construct these things. Given a measurable set E and epsilon bigger than 0, it's sufficient to construct a step function that lies very close to the characteristic function of the set E. And then if your simple function has some linear combinations of characteristic sets, you apply this reasoning. For each one of them, you construct a step function that lies close, and then you just take the sum of all of these things. Okay? Remember, these are all finite sums. Well, but for this, it's very easy, right? We have actually done this, you know. You have a measurable set E. In our case here, my functions have compact support, so I can actually assume that the measure of E is finite. Okay, so really, when we assume that our functions are compactly supported, I'm assuming that all the measurable sets that appear in this function phi are sets with compact support. So you can assume that the measure here is finite. We have seen that we can construct F to be the disjoint unions of cubes Qj from 1 to n, an almost disjoint union, such that the measure of E, the symmetric difference from this E to F, is less than epsilon. And my claim to you is that this function does the job. The claim is that this function psi, to be the sum of the characteristic functions of these cubes Qj, does the job. And essentially because the set where this psi is different from the characteristic function of E is contained in the symmetric difference, or it's contained, I mean, if you have a set here E and a set here your F, which is the almost disjoint union of cubes, I'm just taking the characteristic function of E and the sums of the characteristic functions of cubes. The cubes are almost disjoint, so this is almost the characteristic function of f. Okay? So the set where they differ certainly belongs to the symmetric, it's contained in the symmetric difference. If you have a part in E that does not belong to F, and if you have a part in F that does not belong to E, union some small set, and the set is very small because this function psi here is not exactly the sum of the characteristic functions of the cubes, is not exactly the characteristic function of F, because remember, my cubes are always assumed to be closed, and these are almost disjoint, so you may have two cubes touching in the boundary. So when you have the characteristic function of these two, when you add up, instead of having one, you have two. Okay? So this is certainly, and this might differ from your original set, so this is contained in this, plus, I'm going to say here, boundaries of the cubes. Okay? But again, this set has measure of this set is less than epsilon, and the boundaries of the cubes, the Lebesgue measure of the boundaries of the cubes is measure 0, okay? If you haven't done this exercise, think about it. How do you prove that a hyperplane or a piece of hyperplane has measure 0? Okay, you can cover it by cubes of very, very small volume. Okay? Okay, so then you're done, right? So this is how you do it. Is that clear? Okay, so we get, in the case of RD, something, in general, we can approach by a function monotonically, if you want, by simple functions. In the case of RD, if I give you any measurable function, you can actually approximate this measurable function by step functions almost everywhere. Okay. Okay. So with this proposition in hand, let me prove to you the last one of Littlewood's principles, which is called Lusin's theorem. So theorem, and this is due to Lusin, which goes as follows. Let E contained in RD be measurable set with finite measure. Okay. And let F be a measurable, and let's say finite valued function defined on E. Okay, so I want a measurable and finite valued function defined on E. So I put here finite value just to avoid the infinity or minus infinity. You could have the function being infinity or minus infinity on a set of measure 0. That's fine too, okay? So you can have either a function being measurable and finite valued, let's say finite valued almost everywhere. Function defined on E, if you want. So the claim is then, given epsilon bigger than 0, there exists a closed set f epsilon contained in E, which is very close, such that the measure of E minus f epsilon is less than or equal than epsilon, and such that f restricted to the set f epsilon is continuous. Okay. So this is the conclusion. Any measurable function defined on a set E is nearly continuous in the sense that for any given epsilon, you can find a closed set f epsilon contained in E such that the measure of E minus f epsilon loses to epsilon and such that f restricted to this f epsilon is continuous. I want to make two remarks before we go to the proof. Like I said, first remark is that we can assume that my function f is just finite valued, okay? Everywhere, right? We can assume that my function is just finite valued everywhere. I mean, if you assume that your function is finite valued almost everywhere, there is a set of measures 0 where it may be infinity or minus infinity, you just throw that set away. It doesn't, the result doesn't see that set. You just start working with E minus that set. Okay? So you can assume that your function f is finite valued everywhere. Remark number 2 is more important. So, remember, whenever you are working inside Rd, so if you have a domain X contained in Rd, and you want to consider functions defined on that domain, okay? If I don't say anything else, I'll say, let f be a measurable function defined on X. If I don't say anything else, I am assuming that the sigma algebra that I'm considering are the Lebesgue measurable sets in Rd intersection X. Okay, so if you take any sigma algebra in Rd and you intersect with this particular set X, this forms a sigma algebra of subsets of X. Okay? So when I say a function is measurable in X, I mean this. When I say that a function is continuous in X, I mean a function defined on that set is continuous if and only if the preimage of open sets are open in X. So any set X also inherits a topology coming from Rd. Who are the open sets in X? Are just the open sets of Rd intersection X. So these are the open sets in X. Okay? So what I'm trying to say here is that the function f, when restricted to this set, is a continuous function. This is different than saying, so this is different than saying that my function f is f defined on E, taking values on R, is a continuous function, is continuous at every point of this set f epsilon. This is not what it means, okay? These are two different things. One thing is the function f, when restricted to this set, f epsilon, and taking values on R, is a continuous function. This means that the preimages of open sets will be open sets in this f epsilon set. Okay? This is not the same as saying that the function f, defined in your whole E, will be continuous pointwise at every point of this set f epsilon. Okay?
Second one is strong. Second one.
The second one would be stronger, yes. The second one would be a stronger statement. But this is not always true. Okay? This is not always true. I just want to clarify that this is not what it means. Okay. Okay. So the proof with the elements that we already have at our disposal, we are very well positioned to prove this. Let's see. The first step, the step 1, would be for you to take your function f and you approximate it by a simple function. Okay? So let's say, how do I want to do this? Let's see. Take a sequence like we did. Psi k, approximating f, almost everywhere, psi k, step function. Great. So I can approximate my function f by a sequence of step functions almost everywhere. Second step would be, now, what can I do with the step function? I claim to you that I can take a step function and modify it just in, and consider, you know, let me start over. I can take a step function. For any step function, the set of points where the step function is discontinuous has measure 0. Okay? Because any step function, if you take just one characteristic function of a cube, this function is discontinuous just in the boundaries of the cube. Okay? And then in the rest of the space, it's a continuous function. So if you take just a finite linear combinations of things of this type, the set of points where a step function is discontinuous has measure 0. Okay, so look at this. So the set of points, so in other words, you can construct for each k, we can actually let ek contained in E be such that the measure of ek is small. Let's say measure of ek is very small, say less than 1 over 2 to the k. And psi k is continuous on ek complement. Okay? So you can take just a small piece where it's a very small measure where it's not continuous. So just take this ek is just a small set that contains the boundaries of the cube. And the boundaries of the cubes, you've seen that this is a set of measure 0. Okay, so for each k, you can take a set ek, everything is contained in your E, right, such that the measure of ek is very small, less than 1 over 2 to the k, and this step function psi k is continuous on the complement. Okay. Okay, so now what I want to do is let's consider a set. Let's consider a set which is let's consider step 3. Let us consider okay, I've done this. On the other hand, we can use Egorov's theorem. Well, you have a sequence of functions psi k converging to f almost everywhere. Okay? So, given your epsilon, if I use Egorov's theorem, I can find there exists a set which I'm going to call it f tilde. I'm going to put epsilon over 3 here, such that this sequence psi k converges to f uniformly on the set f tilde epsilon over 3, right? Of course, the set f tilde epsilon over 3 is contained in E. It is closed. And the measure of your E minus this f epsilon over 3 tilde loses to epsilon over 3. Okay? So you can take a closed subset such that the convergence is actually uniform. Now, so you're almost there. You kind of can see where I'm going. So I have selected a set where the convergence is uniform. So if these functions were continuous, if I have a sequence of continuous functions which is uniformly convergent, then the resulting limiting function will be a continuous function. This is what I want to get. Right? So I need these functions to be continuous. So I have to take this set and perhaps eliminate some of these small sets where my functions psi k were not continuous. So the idea is to just take n large, so that if you take your set y to be the union of the e k's with k bigger or equal than n, the measure of y loses to the sums of the measures of e k's, k from beginning on n. This loses to sum of 1 over 2 to the k bigger or equal than n, and this loses to epsilon over 3. So take n big enough such that this exponential, this geometric progression here, starting on big N, loses to epsilon over 3. And you baptize the set y to be the union of these EKs when k is bigger or equal than n. And now you set your, let's say, f tilde to be your f prime to be your f tilde epsilon over 3 that you constructed there, and you want to throw away these guys too. You want to throw away this y. Okay? You want to throw away this y. So in this set here, in this set, you observe two things. So first is that the measure of E minus F prime. So this set is contained in E. This set is also contained in E. So what you have here is you made your E. You have this set which was almost E that you called F tilde epsilon over 3. And you are subtracting somebody which has very small measure. You're taking off a piece here. Okay, so this is contained in E minus this thing is contained in, so this thing here is contained in E minus this set, union y. Okay. That is true, right? Right? So E intersection F prime complement. So what I have is E intersection, and then there's this F tilde epsilon over 3 intersection Y complement. Complement. This is just E intersection epsilon over 3. Complement union Y. And this is just E intersection. A union is just E intersection this guy. Union E intersection Y, which is Y. Okay, so this is good. So this is essentially, this is actually equal to this. Okay? Because Y is contained in E. This, yes, okay. But then, well, we just need this to be included. So this means that the measure of E minus F loses to the measure of this piece, which was less than epsilon over 3. So this is F prime. Plus the measure of Y, which was also less than epsilon over 3. Okay, so you got something here which is 2 epsilon over 3. And on this set that you called F prime, what you have is that this sequence psi j are continuous functions. well, for j bigger or equal than n, right? Because you're removing this set y. So you have a sequence of continuous functions, and you have that they converge to f uniformly. They converge to f uniformly because here the convergence is uniform. And here you are removing the points where the functions psi, j are not continuous. Okay, so you have a continuous function, well, starting at some big n, but who cares, that converges to f uniformly. Okay, so whenever you have continuous functions that converge to a function uniformly, you can conclude that your limiting function is continuous. On this piece, on this space that you fixed here on f. Okay, so you're almost there. You concluded that f is continuous on this f prime. The statement is almost proved, except for the fact that you wanted a closed set. Okay, this set was closed, but when you subtracted some small set here, this whole thing might not be closed anymore. But who cares? You can take another epsilon over 3 and take a closed set inside that guy. So the final step is to just choose f epsilon contained in f prime such that the measure of f prime minus f epsilon loses to epsilon over 3. Okay? And then you put this together with this thing here. So the measure of E minus f prime was less than 2 epsilon over 3. The measure of f prime minus f epsilon loses to epsilon over 3. If you add them up, this implies that the measure of E minus the closed set, this is, you want a closed set, loses to epsilon. And you're done. Okay? So this is the proof of Lusin's theorem. So now you know every measurable function is nearly continuous in this sense. Okay, this is a beautiful, we used Egorov's theorem here, and we used that we could suitably approximate f by functions which are almost continuous in the sense we could use these step functions. Did I really have to use step functions here? Well, I mean, you could try with simple functions. But then a simple function, you might get into a little bit of trouble, right? Because if I give you a measurable set, and if I give you just the characteristic function of a measurable set, and I ask you, well, who are the points where this function is not continuous, The boundary of a measurable set might be something very crazy. Okay, you might have a counter set or something crazy going on, so you cannot really do this step here that you can just remove a set that contains the boundary. The boundary of the cubes are very well behaved, and you can just remove them, and the function is continuous in the other points. But this is not true for any measurable set. So this is how you cannot really start with just simple functions in this argument. This is a beautiful argument. But once you have proved, this becomes now a tool for you to use from now on. Put in your pocket and start using it. You might want to use in one of the homework exercises for next week, this theorem, right? By the way, I'm collecting homework from you today, right? And then the next one is going to be due next Tuesday. So let's keep this routine. Homeworks will be due on Tuesday. I will assign on Thursday. So I will assign on Thursday to be due two Tuesdays after. And then you have lots of fun with Andrea. Okay.
Professor.
Tell me.
I have a question. It seems to me that if I were to embed the non-measurable set, if I were to consider non-measurable set as a subset of R2, then it would be measurable, right?
Yeah, you mean in R, not measurable in R.
If you take a non-measurable set in R, and you look R inside R2, then this non-measurable set is just contained in R, and R has measure 0 in R2. Therefore, any subset of a set of measure 0 in R2 is measurable.
Right,
Yes.
I had a question relating to this. Is there somehow a way to somehow embed spaces of lower dimension into spaces of higher dimension in such that the measure of the image would be positive?
Such that the measure,
Of the image would be positive. So for instance, I could embed R into R2, but then the measure would be 0.
Now, if it's continuous, I think that's not possible. If it's
well, this is a good question. It's not simple. I mean, we have to formulate precisely, but let's see. I know, yeah. I know there are examples of functions, right? That you can take a function, I guess a continuous function from 0, 1 into the unit square that you essentially, that
Yeah,
the
no,
image is dense in the square, right? We can construct such crazy things.
Yes, function
the
and continuous.
Yes.
Piano curve. Piano.
Yeah, this construction of piano, yes. So you can construct really a continuous function from 0, 1, from the interval 0, 1, mapping into R2, mapping into the unit square in R2, such that the image is dense, okay? But this doesn't answer your question. I mean, the image could still have measure 0. Well, if it's a bijection, we'd have to think about a little bit, but yeah, I don't want to go into that discussion of Hausdorff dimension and Hausdorff measure now. We will perhaps enter this discussion more towards the end of the course. But I would have to think about it a little bit, not to avoid saying anything completely wrong. But that's a good question. Think about it with me. All right. Of course, you have to, perhaps for your question to make sense, you have to define how you embed this lower dimensional space into the bigger dimension one. I mean, if it's just a homeomorphism, if it's a continuously
Yes, Professor,
differential, if it's a diffeomorphism or something, and this might make a difference. I'm not saying it makes, but it might make a difference.
Yes, Professor, I was thinking about what he means thinking about the notion of morphism between two measurable spaces, and if somehow a non-measurable set in one space is mapped onto a measurable set in another space, I don't know how exactly to formulate this notion of morphism, but that is what I was thinking.
If you haven't seen this anywhere in the literature, it's probably something hard to do. I don't know. I would have to think about it. I mean, these questions can get very deep, okay? I mean, measure theory in general, or any subject in mathematics, I mean, you can go and you can discuss it for weeks, and it can get as deep as you want if you want to go into the technicalities and understanding the examples and the counterexamples and so on. This is a little bit not the point where I am trying to focus here. You know, I want to give you an overview of the whole thing and giving you, what I feel is the most important in all the subjects. And after that, after these 15 lectures, after these 8 weeks, hopefully you will be confident to explore a lot more on your own. Okay. All right, let me close a little bit our discussion on the Lebesgue measure. And now we are going to try to start discussing, these LP spaces. Okay, this is the main. These are perhaps the most important function spaces for real analysis, okay? So let's have a discussion that starts today and finishes in the next class about these classes of functions and their basic properties. So really, once you have seen this, there will be lots of exercises that you have to do to, complement your understanding of these things. Well, let's try to think about it first in a more generic setting. Okay, so let's go back to the generic setting of having a set omega, a sigma algebra sigma, and a measure mu. Okay, so let this be a measure space. Let's try to think it in general terms. And whenever we feel convenient, we may think about, I mean, the examples that I have in mind are LP spaces of RD or of subdomains of the Euclidean space, okay? So I mainly have in my mind domains or subdomains, either the Euclidean space or a subdomain of the Euclidean space with the Lebesgue measure. But let's try to talk about generically, and for any set, a sigma algebra, and a measure. If needed, we'll see when we have to assume that the measure is complete or sigma finite. Okay, let's see if we have to assume these things to go on. Okay, so when need be, so when needed, we may assume that measure mu is complete, in the sense that subsets of measure 0 are measurable, and or sigma finite, in the sense that the whole space can be covered by sets of finite measure. Okay? Now, okay, so let f be a measurable function in this measure space. And I want to define to you what's going to be the LP norm. Okay, so let me define this following quantity. So let's say here, for 1 less than or equal than p less than infinity, let me define this thing, which I'm going to call the LP norm of a function f, will be just the integral over your domain of the absolute value of f respect to this measure d mu, absolute value of f to the power p, is raised to the power 1 over p. So this will be the definition of the LP norm. We haven't proved yet it is a norm, and this defines a Banach space. We will get to there, okay? But let's just, for any function, any measurable function f, for now just define this object. You take absolute value of f, which is a non-negative function. You raise it to the p, which is measurable function, measurable non-negative function. And then you integrate this. You can integrate any non-negative function. It could be infinity, the result. That's fine. Then you take the power 1 over p. All right? OK. This is if p is not infinity. Well, if p is infinity, let us define
essential boundary.
yes. So let me define this L infinity norm of f, which is sometimes called the essential supremum of f. Okay, so you can either write the L infinity norm or the essential supremum of f. By definition, this is the infimum over the set of alphas, positive, let's say, such that f is less than or equal than alpha mu almost everywhere. You can even say alpha bigger than 0. Okay? It's the infimum of all the real numbers alpha, bigger or equal than 0, such that f is less than or equal than alpha mu almost everywhere, in the sense that the set where this does not happen has measure 0. Okay? Okay, note, I don't know if I have told you this before, but whenever I say that a certain property P holds mu almost everywhere, means that this is the same thing as saying that the set of points x, the set of omega, where this property P does not hold, this set has measure mu 0. Okay? So whenever we say that something holds mu almost everywhere, or simply almost everywhere when the measure is understood, for example, the Lebesgue measure, this means that the set of points where this thing does not hold has measure 0. Okay? So from the definition here, it follows that you can say that your function f of x, say, loses to this L infinity norm mu almost everywhere. Okay. All right. Right? That's true? Yes. That's true. Have this in mind. So the L infinity norm is essentially is a replacement for the supremum of the function, right? But you don't want the supremum, the soup. You want here what we call the essential soup. So what it means is really it's essentially a soup if you disregard sets of measure 0. Okay? So it's something that bounds everybody. So f of x for any x in your set omega loses to this number, to this L infinity norm, mu almost everywhere. So the set of points where this doesn't hold has measure 0, and you may forget it. Okay? All right. So these are the LP and L infinity norms. And before we go, so let's just discuss a few things here. So let me make some remarks. So the first remark is that if you take my functions here, depending on your application, so this function could take values, could really take values on, say, the extended real numbers or in the complex numbers. If you can work with complex valued functions or real valued functions, up to you. But so if you have a constant, say, if c is, say, a real number, or c is a complex number, so the function cf, when you take the LP norm, what you see is that if you multiply by c, you have a modulus of c here to the p, to the 1 over p. So this will be just the absolute value of c times the LP norm of f. Okay? Including the infinity case. Second observation that I want to make to you is that if you add two functions, okay, so I claim to you that, let's say, you may use this inequality here. So if you have two numbers, say a and b, a plus b raised to a power, any power p, this let's say 1 less than or equal than p less than infinity, this loses to, let's say, 2 times the maximum of a and b raised to the p. I don't know if a is bigger or equal than b. So a and b here are non-negative numbers. So this is loses to 2 to the p, if you want. And then the maximum of a and b to the p certainly loses to a to the p plus b to the p. Okay. So a plus b to the p loses to this thing. Therefore, if you apply this to, say, f of x plus g of x in absolute value, this thing here raised to the p loses to 2 to the p, then here f of x to the p plus g of x to the p. Okay, so this implies that if you have, say, the LP norm of f finite and the LP norm of G finite, okay, so when you integrate, if this is finite and if this is finite, then you have that the LP norm of f plus G is also finite. Okay, so this implies this thing. Okay, so you can take two functions. If this number is finite for f, and if this number is finite for g, this number is going to be finite for the function f plus g. So in some sense, the set, if you want to consider the set or the collection of f's such that this LP norm is finite, forms a vector space. Okay? So if you take the collection of functions such that this LP norm is a finite number, you can multiply by scalars and you can add two functions in the space, and the resulting thing will still be in the space. So this is what it is going to be, morally speaking, the space of LP functions. The LP space is going to be the space of functions such that this is a finite number. Okay? So this is a vector space. You can multiply by scalar and you can just add functions. We haven't proved that this is in fact going to be a norm. Okay? So we have to prove that this satisfies the triangle inequality. And also, we have somehow to fix the problem that I'm going to present to you right now, because it's the third remark. So if you have the integral of f to the p mu in omega being 0, okay, so the thing is, maybe you can write this. This is the norm LP, just to include the case infinity as well. So this is going to be 0 if and only if my function f is equal to 0 mu almost everywhere. Okay? So if
By
my,
Chebyshev inequality implies by Chebyshev inequality, неравенство Chebyshev.
yes. Right? So if this thing here is 0, if my function is 0, mu almost everywhere, then the integral is 0. You can check that. On the other hand, if this whole thing here is 0, okay, then my function has to be 0 mu almost everywhere. You can argue by contradiction. If the function is not 0 almost everywhere, the set of points where it's bigger, the absolute value is bigger than 1 over n, for n large enough, will have to have positive measure. Otherwise, you use the increasing sequence of sets argument. Okay, so then the set of points where the value of the function is bigger than 1 over n, for n large enough, will have to have positive measure, and then you will conclude that this integral is positive. Okay, so I'll leave this fact to you for you guys to verify. I might have already assigned this to you in an exercise, right, to prove that a certain integral is 0 if and only if the function is 0 almost everywhere. Okay, so this follows from an exercise that I've assigned this to you. Okay, but the thing is, we have to fix this problem because for something to be a norm on a vector space, I have to be able to tell that the norm of an element is 0 if and only if that element is 0. Okay? So here I conclude that the norm is 0 if and only if my function is 0, but it's just mu almost everywhere. Okay? So you can actually identify functions that are equal almost everywhere. So this is the reason why you do this. Okay, so you identify f and g if f is equal to g mu almost everywhere. Okay, you said that two functions are the same, or equivalent if they are equal almost everywhere, mu almost everywhere. So what you now have is perhaps the class of f. Let's try to denote this. This is the class of the function f. You know, all the elements, all the functions that belong to the same class of, all the functions that are, you can check that this is an equivalence relation, in the sense that f is equivalent to f. If f is equivalent to g and g is equivalent to h, then f is equivalent to h. Okay, so you can talk about the equivalence class of the function f, and you may define the LP norm as just being the integral of f to the p, the mu, omega, 1 over p, if p is not infinity, and the usual modification if p is infinity, right? You see that this integral does not depend on which element of the equivalence class of f you took. If you modify on a set of measure 0, the integral will not change, okay? So therefore, it makes sense to define this as the LP norm of the equivalence class, but we won't be writing the equivalence class all the time. We will simply just abuse the notation and write the LP norm of f, okay? Okay, so in some sense, this LP space, so we can call here LP of omega, okay, for short, or LP of omega sigma mu, if you want, is the space, this is, by definition, the space of equivalence classes f such that norm of fp is finite. Okay? Okay, so this is what the LP space is. Again, it doesn't, I mean, if you take the equivalence class of f and you multiply by c, of course, this is the equivalence class of cf. And if you take the equivalence class of f plus g, this is going to be the equivalence class of f plus the equivalence class of g. It doesn't matter if you change f on a set of measure 0. If you change g on a set of measure 0, you will only change f plus g on a set of measure 0, which is the union of the two of them. Okay? So really, the space of equivalence classes with finite LP norm, this is a vector space, as we defined there, and plus, now, this thing here makes this thing look like a norm. And this is what we are aiming for. Okay? So at the end, ultimately, this LP space will be a Banach space. Okay? What is a Banach space? It's a complete normed vector space. You have to prove that it's a vector space, you have to prove that it has a norm, and you have to prove that it is complete. Complete meaning that Cauchy sequences converge in that space. So this is the outline of what we're going to do. Being a vector space, that's okay. I've seen that I can, if something has LP norm finite, I can multiply by constants, and multiplying by scalar will have the finite LP norm as well. And I can add two guys. If I have two functions f and g, this function will belong to the space too, f plus g. So this is really a vector space. Over R, if you are working with real valued functions, or over C, if you are working with complex valued functions. Okay? Normed. Normed, we are still not there, right? Because this norm here, this thing here, verifies. A norm should verify what? Should verify that an element is 0 if and only if f is 0. That's okay when I identify functions to be equal almost everywhere. What else a norm has to satisfy? If I multiply by a scalar, this should be, I take the scalar out with absolute value times the norm of f. Okay, so this is check. This is check. But the number 3, a norm has to verify the 3 properties always. If you have a norm on a vector space, the norm of an element has to be 0 if and only if the element is 0. The norm, if you multiply by a scalar in your field of scalars, this scalar has to come out of the norm with the absolute value. And third, it has to verify what is called the triangle inequality. Okay, that the norm of f plus g loses to the norm of f plus the norm of g. Okay, this we haven't proved yet, that it verifies the triangle inequality. So if you have a function, right, a function from your space taking values in 0, infinity, function is a norm if it verifies these 3 properties. Okay? We have to prove that it verifies the triangle inequality. The inequality that we proposed here, it's not enough, right? You will have an integral of f plus g, but there will be a factor here, 2 to the p appearing, okay? This might not be the way to go. This was okay to prove that f plus g belonged to the space, but it was not, still not enough to prove the triangle inequality. Okay. Let's see. Okay, so before we depart today, I want to prove these 2 basic inequalities here. Maybe Holder's inequality and Minkowski's inequality. Let's try to do this. All right, so basic inequalities. Proposition. Let me call this, yeah, proposition. Holder's inequality. Let's try to prove this. The claim is the following. I claim to you the following. Let we consider exponents p, q, and r between 1 and infinity be such that 1 over p, 1 over r is equal to 1 over p plus 1 over q. Then you have this. F times g in the LR norm loses to F norm. Let's try to prove this to conclude the class today. Okay? So if you have 3 exponents, p, q, r, 1, possibly infinity, that verify this relation, 1 over p plus 1 over q is 1 over r. Then if you have 2 functions, the norm of f in LP times the norm of g in LQ is bigger or equal than the norm of fg in LR. Okay? Proof. Let's verify this. Let me first get rid of some trivial possibilities. So first trivial possibilities is if the right-hand side is infinity, we are done. These 2 things might be, one of these might be infinity, I am done. Let's assume it's finite. Second, well, what happens if your r here is infinity? If your r is infinity, and therefore p has to be equal to q has to be equal to infinity as well. So you have r be infinity. This is 1 over infinity is 0. So you really want p and q to be infinity. So if the 3 of them are infinity, the inequality is also clear, right? I mean, this f loses to a certain number alpha, G loses to a certain number beta, so F times G loses to alpha times beta. Okay, so this should be also a clear case. So what else? So let's focus on the case. Now let me focus on the case. Let us consider first the case R equals 1 in this inequality, okay? So let's consider the case R equals 1. So I really want to prove, now I have 1 over P plus 1 over Q equals to 1. So in this case, the exponents P and Q are called conjugate exponents, okay? Sometimes, most of the times, you will see Q being treated as being written as P prime, okay? And you want to show that the L1 norm of the product, F times G, loses to the LP norm of F times the LQ norm of G. Okay. If one of them is 0, so if this is 0, this means that F is 0 almost everywhere, then F times G is 0 almost everywhere, okay? So if one of them is 0, you're done. Remember here that we have the convention that 0 times infinity is always 0. Okay, so if F is 0 almost everywhere, if you multiply by anything, it's still going to be 0 almost everywhere. Okay, so let's assume, without loss of generality, that these things are not 0. Okay? Assume that these things are not 0. And this is what we wanted to prove. So this will follow from one basic inequality. So there is a basic inequality that we can prove using calculus, which is the following. Basic inequality that is the core to prove Holder's inequality is this one. If you give me, still before this, I want somehow to excuse the cases. Assume that this is true. If P is infinity or Q is infinity, if one of them is infinity, okay, then it's also clear, because if P is infinity, then you can just, if this loses to alpha, F times G loses to alpha times G. Okay, you can just move this guy out of the integral. So integral of F and G always loses to the sup of F, or the essential sup of F, times the integral of G. Okay. So if one of them is infinity, it is clear. So assume further that the P and Q are really between 1 and infinity, okay? Observe that they cannot be 1, because if one of them is 1, the other one would have to be infinity, and you're also done. So let's assume that you're not in this case. So I told you that this whole enterprise follows from a basic inequality. And the basic inequality is something that we can prove using calculus, you know? If A and B are, say, non-negative numbers, then we want to prove that the product, A times B, is controlled by A to the P over P plus B to the Q over Q. You know? This is a little bit of a generalization of the geometric mean loses to the arithmetic mean. You know, if P and Q are both 2, you would have A squared plus B squared over 2 bigger or equal than AB. A squared plus B squared bigger than 2AB. This is well known, right? This is the arithmetic geometric mean inequalities, you know. This is a kind of a generalized version of this. For any non-negative numbers, P and Q are conjugate exponents. Don't forget. You have that A to the P over P plus B to the Q over Q wins against A times B. How do we prove such a thing? Well, I'll finish this proof and then we're going to finish our class today. Since I already started. Well, this is something that you can prove actually using calculus, right? So, for example, let's consider the function h of x. Let's take one of the variables to be free, let's say a. So let's consider the function h of x to be x to the p over p plus bq over q minus bx. So consider this function of x for any x bigger or equal than 0. Let's try to make the graph of this function. Okay, so then we construct the derivative. H prime of x is just p minus, it's just x to the p minus 1 when I take the derivative. This term here is constant in x minus b. So the derivative is a very easy function to make, you know. It starts negative. Okay, so let's just prove this inequality. If b is 0, you're done. If one of them is 0, you're done. So let's just assume that you may assume here that the a and b are actually bigger than 0. Because if one of them is 0, it's trivial. Okay? So let's assume that b is bigger than 0. And let's graph. So this derivative, h prime, will be a function that starts negative, then it becomes positive. It becomes positive where? What's the 0 of this derivative h prime? Really, there is just one guy. It's this number b to the power 1 over p minus 1. Okay? So this is the root of the derivative. The derivative here is negative, and here it's positive. So if this is the graph of the derivative, this means that my original function is decreasing up to that point, and then it's increasing. So the global minimum, okay, so the global minimum of h occurs at the point x equals to b to 1. And only at this point, okay? It's really only at this point because the derivative here is really negative and the derivative here is strictly positive. So really it increases and here it decreases. So this is the only one global minimum. So this means that h of a, your point a that you wanted in the beginning, is certainly bigger or equal than h of b to the 1 over p minus 1. Okay? And then we have to just plug in here this number. So this is b to the raised to the p, so p over p minus 1 over p plus b over q minus b times x. This looks crazy, but it's not, because remember, you have a relation. 1 over p plus 1 over q is equal to 1, and you can solve it. 1 over q is just 1 minus 1 over p, just p minus 1 over p. So really, your q is p over p minus 1. There will be a lot of simplifications here, because then p over p minus 1 is just q. So really you have b to the q over p plus b over q to the q minus, and then 1 plus 1 minus p minus 1, what is that thing? 1 minus 1 over p minus 1. This is p minus 1, and on top you get p. p over p minus 1 is again q. This is really bq. So bq, b raised to the power q, appears in all the cases, and you have here 1 over p, 1 over q. This adds up to 1. So this is b to the q minus b to the q. This is actually 0. Okay? So you really concluded that the global minimum of this h is 0. So the graph is actually touching here too, at this point. All right. Let's see. So this is the inequality that I want to use. Okay? I'm going to use it in the following sense. I'm going to take 2 points, f of x and g of x. Okay? And I'm going to say that this loses to f of x to the p over p plus g of x to the q over q. So this would be using the inequality with a equals to f of x and b equals to g of x. Right? You can put the absolute value here if you want. But I'm not going to do this. I'm going to allow myself something slightly different. Let me use it with a being lambda f of x and b being g of x over lambda. Okay, so I'm going to put a free parameter lambda here. In a, I put lambda, and in b, I put 1 over lambda, because when I make the product, a times b, this lambda vanishes. But here it will appear. So it's going to be lambda to the p, and here it's going to be lambda to the q. So if you apply your inequality with a lambda bigger than 0 to be chosen later, this is what you get. All right? And then you integrate. Let's integrate this. So then you integrate. So the integral of fg over omega d mu loses to the lambda to the p over p integral of f of x to the p d mu plus 1 over lambda q integral of g of x to the q. Let's write it in the notation of norms. So this is just the L1 norm of fg loses to lambda p. This is just the LP norm of f. Remember, the LP norm of f is this thing raised to 1 over p. So the LP norm of f is this. So this thing is the LP norm raised to the power p. This thing over p plus the LQ norm of g raised to the power q over lambda to the q. Okay. So this is what you get. This is what you get, right? The L1 norm appears here. Here you have the LP norm. Here you have the LQ norm. What's the nice thing about this argument is that this parameter lambda is free for you to choose. So now at this point, you can come here. You say, hey, this is a fixed finite number. This is a finite number. This is a finite number. And then I can just choose my lambda to minimize the right-hand side. So this is what you're going to do. So you're going to choose your lambda to minimize the right-hand side. Right? Because the left-hand side is fixed. It's just this number, which loses to the right-hand side for any lambda. So you will choose your lambda to minimize this right-hand side. Huh. Then this is again a calculus problem. Okay? You just take this as a function of lambda. So this is what? This is a problem which is, well, yeah, you construct this function of lambda. Let's call it big F of lambda, which is lambda to the p, fp to the p of p, plus lambda to the minus q, LQ norm of g to the q. You take the derivative to see what's going to happen, and you make it equal to 0. When you take the derivative, you get lambda to the p minus 1. P cancel with this, times this fp, plus, and then here you get minus q, so it cancels, so you get minus lambda minus q minus 1, g, q, over q. So you want to make this equal to 0, and you want to solve this, right? So you want to solve it lambda to the p minus 1 fpp equals to lambda minus q minus 1 g q q. So what you get is, if I move this guy there, lambda to P plus Q equals to G QQ over FPP. That's your lambda. This is your lambda right here. We're going to choose lambda to be this fella. So G QQ over FPP, this whole thing raised to 1 over P plus Q. When I choose this, so now you'll take this choice of lambda and you will plug in back right here. Let's see what you get. Let's see what you get. So plugging in this lambda, we get that the L1 norm of Fg loses to, now, what is this, let's say, lambda to the p? Well, lambda to the p is this whole fella here, G QQ over FPP raised to the power p, so it's going to be p over p plus q. This whole thing is over p and is multiplying on FPP. And you add up with this lambda to the minus q, so lambda q in the denominator. So let's see how would that be. G QQ over this lambda PP to the q. And the denominator still has a q here floating around. When you simplify this, what you get is, let's see, what do I get? On the top here, I get, what do I get on the top here? G, Q, and here I get PQ over P plus Q. Remember, 1 over P plus 1 over Q is 1. So this is just PQ and then P plus Q. So PQ over P plus Q is 1. So this is going to be 1, the G. And then the F is going to have, the LP norm of F is going to have P minus P squared over P plus Q. Right? So it's P here, and then the denominator have P squared over P plus Q. And again, you can solve this. P minus P squared over P plus Q is going to be P plus Q in the denominator. P squared plus PQ minus P squared. P squared will cancel. You have, again, PQ over P plus Q. So magically, what you have here is just 1, 2. This whole thing over P. And you check this thing here, you also get the same thing. G, Q, F, P over Q. The same thing here, and then 1 over P, 1 over Q. This is, of course, FP, GQ. Yeah. That's your inequality, okay? This is your inequality in the case 1. Okay? So I want to remark to you, well, maybe how you would do the general case. Well, but the general case follows trivially from the case 1. So if you have now 1 over R equals to 1 over P plus 1 over Q, right? And you want to prove that the LR norm loses to the LP norm, the Q norm. So what you do is you just move this R there. So you get 1 is equal to R over P plus R over Q. And you apply, what you have to do is just to apply the case 1 that we did with the functions, so F So if the function say f to the power r and g to the power r. Okay, so if you apply the case r equals 1 with these functions, you get fr times the function g to the r. L1 norm loses to the, now the new p will be p over r. So you have p over r here times g r. And the new q will be q over r. So when you do this, you get the L1 norm. This is just the integral of fg to the r loses to, this is just the integral of f to the r raised to p over r. So this is f to the p raised to r over p times, this is integral of g to the q raised to r over q. Okay, so now it's just a matter of taking root r on both sides. So if you just take root r's on both sides, you finish. All right, so this is the proof of this inequality. I leave to you as an exercise to prove the following thing. So let me just write your exercise to investigate in this proof, actually from what I just erased here, the cases of equality. So this is an exercise for you. Exercise. If the right-hand side of Holder's inequality is finite, equality happens if and only if, let's say, g to the, so the value of g to the q is actually a constant times f to the p, mu almost everywhere. Where? Maybe I can take this, remove this one. What do I want? No, I want this. Yes. Yeah, for some c bigger than 0. This is, let me see if this is what I have. Yeah. C such that g to the q is cf to the p, mu almost everywhere. Yeah. Check that the equality happens just if this function, absolute value of g to the q, is equal to a constant c times modulus of f to the p, almost mu almost everywhere. Okay. Let's finish here today. Ooh, we passed a lot. Sorry, guys. I'll make up next class. Bye-bye, everyone. Thanks for attending. Walter, you can finish the class now. See you next Thursday.